Hello friends, this is Sandeep. So in my last class, in the first lecture of iron carbide equilibrium diagram or iron carbide equilibrium diagram, we have discussed about different invariant reactions occurring in the iron carbide equilibrium diagram. So in today's class, we will be discussing about the phase transformations occurring in hypoeutectoid steel. Okay, so we will be discussing about the microstructure changes occurring in cooling of a hypoeutectoid steel. Okay, so in this class we will be discussing about transformations in hypoeutectoid steel, transformations in hypoeutectoid steels, or we are studying about microstructure changes in during the equilibrium cooling of hypoeutectoid steels, So just for the starting 2 minutes, I will draw the iron carbon equilibrium diagram and I will indicate the different phases present in it. Okay, so which we have discussed in my lecture 1 of iron carbide equilibrium diagram. So the iron carbon equilibrium diagram precisely we are discussing is also called as iron carbide equilibrium diagram, because in the phase diagram we are taking the carbon weight percentage up to only 6.67 percentage. Okay, so that's why we are calling this iron carbon equilibrium diagram as iron carbide equilibrium diagram. Okay, so for the just starting 2 minutes, I will draw the iron carbon equilibrium diagram and I will indicate all the phases present in it, which we have discussed in the lecture 1 or last class. Okay, so in the iron carbide equilibrium diagram, I am taking the temperature scale on the y-axis. In terms of degree centigrade, and composition, that is weight percentage of carbon on x-axis. Okay, so this is the alpha region. I am drawing a horizontal line. Horizontal line indicates there will be one invariant reaction which occurs. Okay, there will be one isothermal reaction which occurs. Okay, so this is the pure alpha solid solution area. Next, this is one another horizontal line. This is gamma solid solution. Okay, next, at this point delta phase exists. So this corresponds to 0.8 percentage carbon. This corresponds to 2.03 percentage of carbon. Okay, so this corresponds to 0.1 percentage of carbon. This is the delta region. Okay, so okay, so at this point peritectic reaction takes place. 0.18 percentage carbon. This point corresponds to 0.55 percentage carbon. Okay, so this horizontal line corresponds to a temperature of around 1147 degrees centigrade, where eutectic reaction takes place at point E. Okay, here this point corresponds to 0.8 percentage of carbon at a temperature of 727 degrees centigrade. We will be getting eutectoid reaction. Okay, so what are the phases over here? Alpha plus Fe3C. Okay, what are the phases over here? Gamma plus cementite. This mixture is called as ledeburite. Okay, so this is liquid. Okay, so what are the phases over here? This is delta plus liquid. Okay, this is delta plus gamma. Okay, so what is the area over here? This corresponds to gamma, and this corresponds to liquid. So this region belongs to gamma plus liquid. Okay, what is the region over here? This line corresponds to liquid. This vertical line of 6.67 percentage carbon corresponds to cementite. Okay, so what is the area over here? Liquid plus cementite. Okay, so now what I will do is I will take a hypoeutectoid steel. Okay, so what are hypoeutectoid steels? Carbon percentage less than 0.8. Carbon percentage less than 0.8. These are called as hypoeutectoid steels. These are called as hypoeutectoid. These are called as hypoeutectoid steels. Okay. So carbon percentage from 0.8 to 2.3. Okay. So carbon percentage from 0.8 to 2.03. These steels are called as hypereutectoid steels. These steels are called as hypereutectoid steels. So what I will do is I will take one alloy of hypoeutectoid steel, that is less than 0.8 percentage carbon. I will show what are the microstructural changes occurring during the transformation. Okay, so let us take some 0.3 percentage carbon steel. Let us take 0.3 percentage carbon steel and we'll study the microstructure changes occurring from austenite phase to the room temperature. Okay, so I will draw the portion of iron carbide equilibrium diagram only in the hypoeutectoid steels range. Okay, why? Because we are studying the microstructural changes occurring for a 0.3 percentage carbon steel. Okay, so I am taking this as temperature, this horizontal axis as composition. Okay, so this is the alpha region, alpha ferrite or alpha solid solution area. So this is the horizontal line corresponding to a temperature of around 727 degrees centigrade. Horizontal line corresponds to a temperature of around 727 degrees centigrade. Okay, so this is the portion of the iron carbide equilibrium diagram. Okay, so this area corresponds to gamma. Okay, this area corresponds to alpha plus gamma. This area corresponds to ferrite region, alpha solid solution. This temperature is around 910 degree centigrade. Okay, so this point corresponds to 0.8 percentage carbon. Okay, so x-axis represents weight percentage of carbon. Y-axis represents temperature plotted in degrees centigrade. Okay, so this point corresponds to how much percentage of carbon? It corresponds to 0.025 percentage of carbon. You all know that alpha ferrite is an interstitial solid solution of carbon in pure iron. The maximum solubility of carbon in alpha ferrite is 0.025 percentage. The solubility of carbon in alpha iron is very less and it can be assumed as negligible. Okay, so that's why alpha ferrite is very soft and ductile. It possesses high toughness. Okay, so I am taking an alloy of 0.3 percentage carbon steel. I am heating to a temperature of austenite region. Okay, I am heating to a temperature of around, say, let us suppose around some 950 to 970 degrees centigrade. Okay, so I have taken 0.3 percentage. I have taken 0.3 percentage carbon steel. I have heated to a temperature of around some 950 degrees centigrade. Okay, so at 950 degrees centigrade, you are having austenite. Okay, you are having austenite solid solution. Okay, so carbon dissolved in FCC iron. Okay, so above 727 degrees centigrade. Okay, above 727 degrees centigrade for the alloy of iron and carbon, the BCC crystal lattice converts to FCC. Okay, so at this point, let us suppose it is T1. Okay, let us suppose it is at a temperature of T1. So what is the microstructure over here? Carbon is dissolved in FCC iron. Okay, thus you are getting gamma solid solution or austenite. Okay, so what is the microstructure? So the microstructure looks as entire austenite. Okay, so the microstructure looks as entire austenite grains. Okay, so this is the microstructure which is which consists of entire gamma grains. Okay, entire gamma solid solution. Okay, so this is gamma solid solution. So in this austenite, how much percentage of carbon is present? It is 0.3 percentage carbon. Okay, now I am doing equilibrium cooling or slow cooling. Okay, so when I am doing equilibrium cooling or slow cooling, nothing happens until this point is reached. Okay, why? Because from this point to this point, all the grains are gamma. Okay, all the solid solution is gamma solid solution, that is austenite. Okay, so from this point to this point, from this point to this point, under equilibrium cooling, nothing happens until this point is reached. Okay, let us name this. Let us say this point is G. Let us say this point is S. Okay, when it touches the point on the GS line. Okay, what happens? Now ferrite starts forming. Okay, so at this point, let us say the point is T2. Let us say that point is T2. The ferrite starts forming. Along the grain boundaries of austenite. Okay, the ferrite starts forming along the grain boundaries of gamma. Why? Because the grain boundaries are the sites which are easy for nucleation. Okay, so how the microstructure looks? So at this point T2, so along the grain boundaries of austenite, ferrite starts forming. Okay, so this is the portion where ferrite starts forming. Okay, so I'm indicating ferrite along the grain boundaries of austenite. Okay, so I'm indicating like this. So this corresponds to alpha ferrite and this corresponds to austenite, gamma grains. Okay, so you can observe over here, below this point ferrite starts forming. Okay, so ferrite contains very less percentage of carbon. Okay, so the carbon which is present must come out of the solution, then only it can form ferrite. Okay, so the carbon comes out of the solution and it dissolves in the remaining austenite. Okay, the carbon comes out of the solution and it dissolves in the remaining austenite. Okay, that's why when you do slow cooling, okay, you can observe over here the carbon percentage in the gamma gets increased. Okay, and it reaches to a maximum of up to 0.8 percentage of carbon at a temperature of 727 degrees centigrade. Okay, so so before the iron atoms arranged into BCC lattice, that is alpha ferrite, the carbon comes out of the solution and it dissolves in the remaining portion of the austenite. Okay, so thus upon equilibrium cooling, the portion of ferrite gets increased. Okay, and the carbon which comes out of the solution is getting dissolved in remaining austenite, and the austenite is getting enriched in carbon. The austenite is getting enriched or more amount in carbon, and it reaches to a maximum of up to 0.8 percentage of carbon at a temperature of 727 degrees centigrade. Okay, so the carbon atoms comes out of the solution and it dissolves in the remaining austenite. Okay, thus forming alpha ferrite. It is called as pro-eutectoid ferrite. So suppose if I take a point over here. Okay, let us say this point is T2 dash. So at point T2 dash there is some pro-eutectoid ferrite which is formed. Okay, so how the microstructure looks? It looks like, so I'm drawing the microstructure at this point T2 dash over here. Okay, so the microstructure looks like this. Okay, so it contains gamma grains and pro-eutectoid ferrite. Okay, So the microstructure looks like this. So please see over here. So it contains alpha ferrite, that is pro-eutectoid ferrite. Okay, it contains alpha ferrite, pro-eutectoid ferrite, and it contains gamma solid solution, that is austenite. Okay, so this is gamma. Okay, this is gamma. Okay, so upon equilibrium cooling or upon slow cooling, when this point is reached, when the temperature of 727 degrees centigrade is reached, the gamma solid solution, the austenite, is not stable below 727 degrees centigrade. Okay, so whatever percentage of austenite which is present at temperature of 727 degrees centigrade, it converts to pearlite. Okay, so once this point is reached, what happens? The percentage of austenite present at this point converts to ferrite plus cementite, because of the eutectoid reaction, So this eutectoid mixture is called as pearlite. Okay, this eutectoid mixture is called as pearlite. So this eutectoid mixture is called as pearlite. Okay, so at this point what happens? The austenite present converts to pearlite. So how the microstructure looks at this point? So it looks as pro-eutectoid ferrite plus pearlite. Okay, so if I draw the microstructure, I'm drawing over here. So the microstructure consists of ferrite and pearlite. Okay, so what is pearlite? Pearlite is a eutectoid mixture of ferrite and cementite. Okay, it is a matrix of ferrite and cementite. Okay, so this portion is pro-eutectoid ferrite. And the rest of the portion is pearlite. So pearlite, the shape of the pearlite is like your fingerprint shape. Okay, lamellar shape. Okay, shape of the pearlite is lamellar. Okay, so it is a matrix of ferrite and cementite. Okay, so pearlite is a matrix of ferrite and cementite. Okay, so I'm drawing the microstructure. I'm drawing the pearlite, that is ferrite and cementite. Okay, so you can say this white portion is ferrite and this dark portion is cementite. Okay, so cementite is 6.67% of carbon in iron. It is an interstitial compound. Okay, so until the remaining austenite present at this temperature is not converted to ferrite and cementite, the temperature cannot drop. The temperature cannot be decreased. Okay, so at this point, how much percentage of pro-eutectoid ferrite and how much percentage of pearlite is formed it can be calculated by means of lever rule. Okay, so what is lever rule? Lever rule states that amount of phase present is inverse of its length. Okay, so at this point, okay, how much percentage of carbon we have taken? 0.3% of carbon. Okay, we will find out how much volume percentage of pro-eutectoid ferrite and how much volume percentage of pearlite is present. Okay, so how we are getting pearlite? Because the gamma gets converted to ferrite and cementite. Okay, why? Because gamma is not stable below 727 degrees centigrade. Okay, so with the help of lever rule, you can find out the volume percentage of these phases present in the microstructure. The percentage of pro-eutectoid ferrite and percentage of pearlite. Okay, alpha plus Fe3C. Okay, so if I apply lever rule, okay, to find the lever rule, to find the percentage of phases present, okay, to find the volume percentage of phases present in the microstructure. Okay, so I'm taking 0.3 percentage carbon. I'm taking 0.3 percentage carbon. Okay, so this is 0.3 percentage carbon. So if you draw a horizontal tie line, okay, at this point, okay, it meets the alpha line. It meets the alpha line. What is the percentage of carbon here? 0.025. Okay, this is 0.025. Okay, if I move to the right, okay, I can meet the gamma line, which is getting converted to pearlite. Okay, what is the percentage of carbon over here? 0.8. Okay, this is 0.8. Okay, so by applying lever rule, what is the percentage of ferrite? Percentage of ferrite is equal to 0.8 minus 0.3 divided by 0.8 minus 0.025 into 100. Okay, so how you got this? Lever rule states that amount of phase present is inverse of its length. Okay, so that's why I have taken 0.8 minus 0.3. Okay, so it is equal to, it comes around some approximately 64.5 percentage. Okay, so what is the percentage of pearlite present? Percentage of pearlite present. Okay, so it is equal to 0.3 minus 0.025 divided by 0.8 minus 0.025 into 100. It comes around some 35.5 percentage. Okay, so in the microstructure, the percentage of ferrite present, the percentage of pro-eutectoid ferrite present is how much? 64.5 percentage. Okay, so these hypo eutectoid steels are majorly used for structural applications. Why? Because this hypo eutectoid steels consists of pro-eutectoid ferrite, which is soft. Pro-eutectoid ferrite, which is soft, and it consists of cementite, which is hard. Okay, with pro-eutectoid ferrite you are getting good ductility and toughness, and with cementite you are getting strength. Okay, so the microstructure decides the properties of the material. Okay, so we are getting in the hypo eutectoid steels, we are getting both toughness and we are also getting strength. Okay, so that's why the hypo eutectoid steels are majorly used for structural applications. Okay, like in houses, like house construction. Okay, shipbuilding. Okay, so that's why the hypo eutectoid steels finds variety of major applications. Okay, so that's all for regarding the microstructural changes occurring during the equilibrium cooling of a hypo eutectoid steel. Okay, so what we have discussed is, when we heat the material up to austenite region, we will be getting gamma solid solution, that is austenite solid solution at this area. Why? Because at higher temperatures, for 0.3 percentage carbon steel, at this point austenite is in stable condition. Okay, so upon equilibrium cooling up to this point, no changes occur. Okay, so at this point what happens? Slowly the ferrite starts forming along the grain boundaries of austenite. Okay, ferrite starts forming along the grain boundaries of austenite. Okay, why? Because grain boundaries are the best sites for nucleation. Okay, and upon equilibrium cooling, what happens? Pro-eutectoid ferrite starts forming. Okay, so the carbon comes out of the solution and it forms pro-eutectoid ferrite, which contains very less percentage of carbon. Okay, so upon equilibrium cooling up to this point, what happens? The gamma how much whatever present, okay, it decomposes to ferrite and cementite, which is called as pearlite. Okay, so thus the resultant microstructure consists of pro-eutectoid ferrite and pearlite. Okay, so the percentage of phases present in the microstructure, which decides the properties of the material, are found out by lever rule. Okay, so that's all for today, and in my next class we'll be seeing the microstructure changes occurring for eutectoid steel and microstructure changes occurring for hyper eutectoid steel. Okay, thank you.